As if that wasn't enough, there's a little bit more weirdness to special relativity. So let's go back. Suppose you're standing on the sidewalk and I zoom by on my bike. And I don't know why, I got a picture to show it, but for some reason I'm zooming by and I'm holding a meter stick so that the meter stick is parallel to the ground. That's the new wrinkle I'm adding. As we talked about before, if you could see my watch, the watch would be ticking a little bit slower because I'm moving through space. I've stolen some of my space-time motion away from the time component. The fancy name for that is called time dilation because a little of my time is spread out over more of your time. Like your pupils might dilate, my time has dilated. My time has spread out. The little bit more is if you could get a good look at the meter stick would actually look shorter. It would look like it was less than a meter long. An explanation for that is to see the meter stick, light needs to reflect off the front of it and get to your eyeball, and light has to reflect off the back of it to get to your eyeball. That's how we sort of see the length of the meter stick. But if I zoom by on my bike, the reflected light that allows you to locate the front of the meter stick, the reflected light allows you to locate the front, but by the time it takes for the reflected light to allow you to locate the back of the meter stick, the back of the meter stick is moved. So you figure out where the front is because the light bounces off of it, but there's that little time delay because of the speed of light. It's going to be tiny, but there's a little bit of a time delay for you to locate the back of the meter stick, and in that little bit of time delay, the back of the meter stick is moved. So we see the meter stick, or you see the meter stick as being shorter. That weirdness is called length contraction. When things are moving crazy fast, time gets dilated and their length gets contracted. Last little piece. If I'm zoomed by on my bike really fast and I wanted to accelerate my bike or make it go even faster, it always takes a force to accelerate, basically F equals ma. But if we did the math on it, the force it takes me to accelerate is a little bit larger than F equals ma predicts. So if I wanted to accelerate, it takes a particular force to make that happen. If I zoom by crazy fast, it takes a little bit more force than expected. According to F equals ma, if it's taking more force, something on the right must be bigger. If it's a particular acceleration giving a bigger force than expected, that means the mass has increased a little bit. So this is a weird one. Just because of the motion relative to you, I seem to behave as if I have more mass. If we were to do like an F net equals ma calculation, the F number would be a little bit bigger. If I were to do a little crash and we had to do conservation of momentum, I'm behaving as if my mass is a little bit bigger. This weird one is called the inertial mass increase. I haven't actually gained any matter. I'm just behaving inertia-wise. I'm behaving as if I have. So since I'm behaving as if I'm a little bit heavier, it takes a little bit more to accelerate me. So special relativity really has three parts to it. Time dilation, something going really, really fast seems to be ticking through time a little bit slower. Length contraction, something going really, really fast seems to be slightly shorter from front to back. And this thing called inertial mass increase, something going really, really fast behaves as if it has more kilograms than it actually does. Cool little diagram to emphasize it. Clock's going to tick slower. If I'm not moving, clock ticks the same, meter stick looks the same, mass is the same. But if I zoom by quickly, clock's a little slower, meter stick's a little shorter, and I behave as if I have more mass. The faster I go, the more it gets emphasized. Clock ticks even slower, meter stick looks even shorter, and F net equals ma, I behave as if I have even more mass. Basically, this is kind of a neat one. The faster you go, the more mass you seem to have, which means the faster you go, the more difficult it is for that object to go faster again. So basically, going fast makes it harder to go even faster. We'll see, there's a math proof to it later, but basically this statement here that going fast makes it harder to go faster builds in a universal speed limit. There's a speed that objects reach, and it is mathematically and physically impossible for them to go any faster. Practically, it's impossible because the faster you go, the harder it gets, and they just basically get to a point where it's impossibly hard to go any faster. I'm going to pause this video. The last cool thing, we're going to do a little bit of math next. Um, those three quantities, time, length, and mass, when they change, they all change by the exact same factor. If I zoom by in a spaceship going so fast that 60 seconds tick by on your watch and only 20 tick by on mine, that's what you observe from standing on the sidewalk, the time dilation, we would say that's a time dilation factor of 3. Since 60 seconds on your watch divided by 20 on mine, 60 divided by 20 is 3. That's a time dilation factor of 3. What that means is that if the time is ticking slower by a factor of 3, then my spaceship would look shorter by the same factor of 3. If my spaceship was like 30 meters long when it wasn't moving, you would see it as if it only was 10 meters long. If the spaceship behaved as if it had a mass of, I don't know, 1 billion kilograms, when I'm going that fast, it would behave as if it had a mass of 3 billion kilograms. The factor depends on the speed. We're going to do that next. The faster the object, the larger that factor is. At everyday speeds, the factor basically works out to 1, so we don't see a time, length, or mass change. But as things go crazy, crazy fast, the faster it goes, the bigger that factor, the slower time looks, the shorter lengths look, and the more massive things behave like.